my diploma thesis on some aspects of loop quantum gravity, and then I did a PhD in mathematics, something on operator algebras, and I became interested in the Cauchy-Specker theorem, and this is how I made contact with Chris Isham. And now I'm at Imperial College since December. And what I will be talking about is, well, joint work with Chris Isham, and of course he has been working on Topos ideas and then importing them to physics much longer than I did, obviously, but now we're making some progress again with what he started some years ago. Okay. I want to start very, very basic. Say something about phase spaces and Boolean logic. Namely, if we have classical physics, then physical quantities or observables, and I want to avoid the word observables. Chris always objects when I use that because it already carries with it all this stuff about measurement, and so we want to get away from that a little. Simply say physical quantities, but if you like observables, then think of observables. Well, they are simply described by functions on a phase space P, and this can be some manifold. Just this block here and going to the real numbers. So very, very basic. And of course, the points of this phase space are something like pure states, or in classical physics we usually don't call them pure states, but that's just what they are. If I have observables, then each point assigns values to them. So this is exactly why we're going down to real numbers. Of course, we can turn the view around also and then consider level sets, which would be inverse images of some points here on the real axis, or more generally inverse images of some subsets. And I show some delta here, which is an interval, which is the simplest example of a subset. And so the inverse, of course, goes up. It's not a function anymore, but still I show this error here, and then we get some subset of phase space. And such a subset of phase space corresponds to a proposition of the kind A is in delta, which is to be read as the physical quantity A has a value lying in the set delta. There's absolutely no problem with that in classical physics. We can do that, and of course this set here simply corresponds to all the states in which the observable A has a value lying in delta. And then, well, this is really simple. Each point of phase space either lies in such a set or it does not. So you can say for each point the proposition is either true or it's false. And we have two propositions, A is in delta 1 and B is in delta 2. The corresponding subsets, then of course we can take the intersection, and this will correspond to the proposition A lies in delta 1 and B lies in delta 2. The union corresponds to the OR, and the complement corresponds to the negation. So what I emphasize here is that classical physics is based on a Boolean logical structure, which basically is the Boolean lattice of subsets of phase space. I haven't been explicit here in any sense if we want to consider continuous or differentiable functions. So this is just a very general way of looking at that. But if we have classical physics, we do have Boolean logic built in. And of course one can ask, and this has often been asked, if quantum theory can be formulated in a way similar to that. And so the problem is there a phase space, usually called space of hidden states, for quantum theory, such that physical quantities are real valued functions. We still want to assume that our physical quantities take values in the reals. These functions usually are called hidden variables on this space. And there's much discussion that's still going on. And of course the self-adjoint operators that we usually have, like in some phenomenon algebra here, I'll say something on that in a moment, should somehow be embedded. So they should lie in this set of functions which are hidden variables. I throughout want to assume that we have some phenomenon algebra there. if you know what this is, it's okay. If you don't know it, for R you can always read all the bounded operators in Hilbert space. And phenomenon algebra is a weakly closed operator algebra which is contained in some L of H or L of H are the bounded operators on some Hilbert space. And if you have symmetries in your quantum system or sort of selection rules, then it's a good thing to use phenomenon algebras. So you also probably know that. If you consider this problem as Koch and Specker did, then you find that a necessary condition to have such a phase space model would be that you have valuation functions. What is this? This would be functions while sending self-adjoint operators to the reals in the following way. V is such a function, A is such an operator. Of course, the V of A should be some element of the spectrum of A. I think this is quite clear. But then, not all the operators are independent. You can take functions of operators. And then you would want that evaluating the function g of an operator is the same as first evaluating the operator and then taking the function on the reals. And this is a sensible formula because you can apply REL functions to operators in phenomenon algebra as well. And this is the famous func principle, and although this looks very natural, it's a very, very strong condition. And in fact, it leads, it can be shown that there are no valuation functions. So this is what Koch and Specker did in 1967. And they showed this when the phenomenon algebra actually is L of H, all the bounded operators in Hilbert space, and the dimension is at least 3. And originally it was quite a complicated argument. They took real three-dimensional space, which is okay, and then they took 170 lines in Hilbert space and showed by quite complicated combinatorial argument that there can be no valuation function for that case. And the number of vectors could be reduced to 31, I think, and there are lots of papers on that. I learned that there are whole classes of counterexamples by now, but still it's a proof by giving counterexamples, basically. In 2004 I gave a different proof using functional analytic techniques and then basically showing that this comes down to Gleason's theorem, namely having a valuation function would mean having a state, and this state would have properties which violate these conditions. So it's a proof by contradiction, and this can be generalized to all phenomenon algebras, except of course the Boolean ones where we do have valuation functions, and those of type 1, 2 must be excluded. And this is corresponding that the original theorem dimension 2 is excluded also. So we really hit the wall here in some sense, because there is no naive realistic model of quantum theory where we could expect that all the observers have the same values. And this is really showing that quantum theory is very, very different from what we're used to in classical physics. And, so what can we still do? What becomes of realism? Or what can we do? And as I already mentioned, there is no problem if we have a Boolean phenomenon. This is no surprise, after all. There, the Gelfand spectrum would play the role of the space of hidden states, and the Gelfand transforms would be the self-adjoint operator. Would be the hidden variables, the Gelfand transforms of self-adjoint operators, I should say. And then, just to introduce the notion of what most of you really know, that these abelian subalgebras, I always assume that all the phenomenon algebras are a unit, they have a unit. They are called contexts, and so the Koch-Specker theorem usually is read in a sense that we need some kind of contextual model of quantum theory. But I want to emphasize here that what Chris and I are trying to do is also to gain a very good control over the relations between different contexts. We should not go ahead and do different things in different contexts without any relation between them. After all, there are relations, and we want to formalize this in the following way. Butterfield did this